Hello, everyone. Very good evening to all of you. I'm in Mumbai. I don't know where the rains have gone in this week or the past week. If you are having good monsoon, do send them here. We're experiencing a dry spell over here. So welcome to the Knowledge Series 2019. This is a platform that brings experts from industry and academics to share expertise, ideas, knowledge about projects, products, technologies, etc. to fuel discussions on building energy efficiency and grow engagements for net zero energy buildings. This initiative is brought to you by the METRI program funded by USAID. METRI stands for Transformation, Market Integration and Transformation for Energy Efficiency. You can know more about the program on our website, metri.edsglobal.com. Today, we are going to talk about a very, very interesting building, a project, which is at CEPT University. It's a lab. And we are going to focus on what does it take to operate a building to ensure the net zero goal is maintained over time. And a little bit about me, I'm Deepa, I'm an architect and a green building consultant, and I will be the session moderator today. And joining me from Ahmedabad are two expert speakers, Professor Rajan Rawal and Dr. Yash Shukla. Let me introduce them to you. Professor Rajan Rawal is the Executive Director of the Center for Advanced Research in Building Science and Energy. This also we call as CARBSE, and that's the building we're going to actually discuss about. He is an architect, and his work emphasizes on the energy performance of buildings and cities and architectural science education. This is his area of focus. He is involved in research and development activities at CEPT University and coordinates the activity of CARBSE. He is the founder member secretary of Indian chapter of International Building Performance Simulation Association. A lot of us call it as IBIPSA, and also serves at the IBIPSA World Committee. He has a number of research papers, technical reports, and 3 books to his credit. Rajan Bhai is a very well-known authority in the area of building energy efficiency and performance. Joining him is Dr. Yash Shukla. He is the technical director at CARBSE and also an ECBC master trainer. He is a mechanical engineer with more than 15 years of international experience in building energy efficiency research and serves as a lead on several energy efficiency research projects at CARBSE. He also has extensive experience in building management systems, building energy analysis, HVAC system operation, component characterization facilities, development of test chambers, building simulation modeling, and energy efficiency control algorithms. His prior work experience also includes providing technical support in designing and implementing commercial and residential energy efficiency programs throughout the US. So today we're going to have Rajan Bhai talk about the design and construction of the CARBSE facility, and Yash talk about the operations side of it. I welcome both of you to the session today, and from this point on, Rajan Bhai, you can start with your presentation.
Thanks, Deepa. Welcome all of you to this webinar on NZEB, and probably I'll be talking about, as you can see on the screen, I'll be talking about work which we have done on the campus, as well as how are we occupying and managing the buildings. A little bit of background, and what I'll do is I spend about 20 minutes talking about why and what we did before handing over to Yash. and giving him certain kind of challenge to operate building in a NetZDB fashion. So I will probably, yeah. So I think this is a sort of repeat of many of you who are aware and working in a building energy efficiency sector that our consumption in space cooling is going from 135 to 600 terawatt hour by 2037, and our per capita cooling consumption is also increasing. What is very interesting is that we have a range of buildings in front of us, either built in a medieval time or during modern architecture period when it was peak, or something which we have started seeing recently. And this is a sort of response to the kind of climate which we have seen in a recent time. And hence the kind of opportunities we have and kind of solutions which we have tried to attempt it, that sort of drives what we call it in academic is how do we see the future of buildings. And that's what the context of the CARBSE building is basically sits on the campus of CEPT University, which is sort of a significant place in a modern movement when Professor Doshi started in 1962. And recently we have started also adding few buildings which does have a response to a climate. As you can see here, not only just outdoor but indoors, but also we have sort of started looking at spaces like library and workshops. As many of you would have noticed that CEPT University is a habitat university, and we focused more on understanding, designing, planning, and construction of buildings and cities. So that's what the context in which CARBSE sits in is basically a research center within the part of the university, which focuses on research and development related to building physics, thermal comfort, IT in buildings, low energy cooling, and we work on design, technology, and policy space. You may visit www.carbs.org later on whenever you get time to know about what we do. And last October, we celebrated our 10th year anniversary. So the logo which you see here is actually the cross section of the NetZEB, and you will recognize that once you see the drawings of the buildings later on. A little bit about site and when we started. Some of you might be able to recognize the patch which is you're seeing in the right hand side. This is I think 14th January 2007 picture, which was a kite flying day, and that's a place where we have constructed a building, which at that point in time was on a southern part of the campus, but now campus has also expanded, so now it has come almost in the center of the building. And what you see in the center is one of the manifestation of our one of the faculty members who actually depicted the site, which again you can see next to the Hoshidushen Gufa, is a NetZEB in a miniature format, in a Madhubani format rather, I would say. Coming on the design of building, we started operating from about a space which is about 30 feet by 30 feet, and when we started expanding, we thought that let's build a building. But again, people whom we interacted with, and especially some of them who were involved at the USAID ECO program at that point in time, and the leadership of EDS Tanmay was also engaged in some of the discussions here, is that when we started expanding, we thought that let's build a building which itself can help us understand the subject which we are dealing with. Not only it will house few people and few equipment, but also it will help us understand the kind of performance which we want to understand in at least in hot and dry climate of India. And it also should be able to demonstrate various technologies and feasibility of these technologies, not in a technical form, but also in economic form. So we started relying on a design charrettes. We had about 3 design charrettes in Ahmedabad on campus, where all sort of consultants and funders and everybody were present. And later on, we conducted about 50 virtual meetings and presentation to come up with the design, and we were monitoring the progress. So during pre-design stage, before we met, USAID program was on, and USAID ECO 3 program helped prepare the pre-design document. And during the charrettes, we worked on conceptual design and then system development, and later on system optimization part. And I'll not go into details of this, but because the focus is more on what is this building and how are we sort of operating. We followed typical process which generally you see in an architectural office. Professor Doshi was guiding us. We made various kind of material models, the clay or thermocol or refined clay and so on and so forth. And then we also started relying on simulations, trying to understand what are the options and what are the end use you may envisage if you start relying on certain options. So we did a bit of massing exercise, trying to understand. Fortunately, the site was such that it wasn't offering us too much of flexibility. And in fact, to some people, it was a challenge. For some of us, it was sort of benefit that that we didn't want to think too much about the orientation and so on and so forth, because site itself was helping us to orient building east-west longer axis. When we started looking at thermal comfort and shading, again, a lot of you would be aware about the kind of shading mask we use. And we also started not only targeting what kind of energy efficiency we want to achieve, but we also started targeting how much comfort we want to achieve. And this is a time where our India model for adaptive comfort was still under research stage. So we relied on ASHRAE 55 equations to understand what would be the comfort range in Ahmedabad if this building gets operated in a naturally ventilated mode. So what you see on left hand side is a graph where in the black you see outdoor conditions, and light yellow where you see comfortable condition at 80% acceptability. And then we started doing a bit of zoning, and the bottom graph which also suggests that how many hours in a year at various places, at various levels, a person can be comfortable. The white group, which was involved with us since beginning, they conducted certain kind of daylighting analysis and sun control analysis, especially when we decided that we want to face south, primarily to harness sun and install solar photovoltaic. What would be the effectiveness of light shell for a clear story? And if at all we decide to go for it, what should be the dimension of it? So what you see on the left hand side is again the various kind of options, and on the right hand side the effectiveness of it, how much diffused light which will get in at occupant hours and so on and so forth. So again, not only just shading and daylighting, but we primarily rely on useful daylight index analysis to understand what would be the effective aperture. And once we decided that, what you see here is that selection of a glass, which was on up top, you can see it was 67% VLT, and the bottom, what you see, the 33% of VLT. This is a section for the basement, and to understand what would be the impact of a glass once we decide the aperture systems and so on. Primarily because we also wanted to operate building as much as possible in a naturally ventilated mode. We rely on computational fluid dynamics to understand what will be the PMV PPD. Again, this was as per ASHRAE, and what you see here is cross-sectional and planar diagrams about various temperatures when we start operating windows, when we don't operate window, and if we start relying on an air conditioning mode. So these are the sort of studies which we did. We also at one point in time thought of relying on a radiant cooling system, but the radiant cooling system which can which can rely only on stored water from the rainwater harvesting. This is not a system which we have adopted. Finally, we do have a radiant, which we'll talk about later on, but the radiant system is not completely based on water stored from rainwater harvesting. So many things which we did at the study, and that's what the power of simulation, that's what the power of IT. It helps you to decide what you want to do, and hence, as you can see here, we relied on some of the building information modeling, even to sequence out the construction and so on and so forth. So it was a time when we decided that we have a reasonable amount of options available with us. We need to decide what should be the target. So during those 6-8 months, we did study buildings around CEPT campus having similar kind of, on the CEPT campus and around CEPT campus having similar kind of occupancy and similar kind of work of nature. So basically, we look at the colleges around, we looked at NID, we looked at IIM, some of the elite schools as well, and we found that probably typically 237 EPI is what people consume, and then based on the availability of a site on which we can install solar photovoltaic, and a kind of loads which we'll have and kind of buildings which can construct, we came to a target that probably this building should use about 60 kilowatt hour per meter square a year. And with that sort of technical potential, we say that let's move forward and start identifying construction technology and start identifying HVAC system and so on and so forth. So this was sort of target which we set after we did reasonable amount of study and feasibility. So finally, lot of work which we did based on economics and based on feasibility of construction and speed of construction, workmanship, kind of people available, and the age of the various materials and so on and so forth. What you see here on the screen is construction which we adopted finally. One of the challenge and also means an opportunity for us to experiment was at that point in time, there was a mandate on a campus that all buildings externally must have exposed brickwork. So what you see on extreme left is a wall which is of a superstructure having half a brick thick wall as a fascia, and then XPS inside, and 230 mm brick as a main wall inside with the plaster. While we were doing this, entire exercise was based on a philosophy that we must harness our outdoor condition as and when it's allowed for us to harness it. Hence, the building, basically what we have is a temporal mixed mode building. Temporal mixed mode building means the building which uses outdoor air as it is without any treatment whenever it is favorable. When it becomes harsh outdoor, we close our windows and we start operating various kind of air conditioning system. We just don't have one system, but we have multiple system, and depending upon the need in outdoor conditions, we operate these systems. So that means that the building must have a high performance in terms of envelope. But at the same time, whenever we start operating that on a naturally ventilated mode, we should have enough thermal mass which gets charged over a period of time and can help us retain lower mean radiant temperature for extended period of time. So that's why you see 230 mm brick wall inside. Structurally, it wasn't required, but just to increase thermal mass, we thought that let's have that. And now, after 4 or 5 years of operation, we feel that it was a very good decision which we took at that point in time. Roof again was heavily insulated. It is a sprayed PU foam on top of RCC. Fortunately, we got a product, and I don't mind talking about this because it wasn't. We don't have any commercial interest, but a Pidilite is having a product where they take a guarantee of waterproofing, insulation, and cool roof coat on top. So that's what we adopted, primarily because the cross section of the top RCC slab was such that any kind of boarding or any kind of coating might have developed a cracked over period of time. So hence we relied on sprayed PU foam to get a uniform and monolithic layer on top of the RCC. So what you're seeing here on the screen is a ground floor. Basically, it's a building having about 3.5 floors. When I say half floor, it's basically mezzanine. Professor Doshi wanted to not only provide efficiency, but he said that the kind of objective you have, that a building definitely needs to have a net zero status, but at the same time the occupants and visitors must be able to experience various kind of environment at one point in time. So hence the basement came into the picture. Basement is a completely air conditioned building, or air conditioned space rather, having a radiant and a dedicated outdoor air. And then a ground floor which is semi-open, which floats around with the outdoor all the time. And first floor and a mezzanine floor, where first floor we have our laboratory equipment and few researchers sit there, and mezzanine is primarily a desk space with all about 22 researchers sits there. So that's a volume which is we are operating in a mixed mode operation. That means that basement is air conditioned, ground floor is naturally ventilated, and first and mezzanine floors are getting operated on a temporal mixed mode operation. So this is what you see on a section, longitudinal and cross sections. As I was mentioning, the basic philosophy of construction and operation was a mixed mode building. It means that whenever you have a favorable outdoor, you let the cool air get in. Whenever there is a harsh outdoor, you just close yourself, start relying on conditioning system. So to the students, generally what we say is that this is a building which uses conductive heat transfer principle, not to let heat get in, because that's where the building is completely sealed. But then at the same time, whenever outdoor is comfortable, we rely on convective currents to cool the buildings. And this is how we teach students that where a conductive current will help and where the conduction will help, or you need to manage the conduction in a reasonable manner. This is how it looks from outside. When we started installing various kind of research equipment at the same time, the equipment which serves the building, as we thought that let's try to make them more aesthetically pleasant. Also, they simply should not sit as alien machines on top of the building or inside the building. They also should merge with the landscape around it, also should comprehend and sort of have a synergetic aesthetic value with the outdoor. So what you see here is one of the air handling unit sitting near the staircase which leading up, and on right hand side what you see is a walkway which is facing a north rather, and as you can see, ground floor is naturally ventilated, and first floor you see windows which are operable windows. This is how it looks from the southern side. Yeah, somebody may comment that the tree is shading the solar photovoltaic. It's actually not. In the picture it does look. Even the right hand side picture, it looks that this building is getting heavily shaded by trees, but it is not. In picture it looks, although the right hand side picture looks like this building is somewhere in Mahabaleshwar or Panchgani. It is not. It very much sits in a hot climate of Ahmedabad, and it functions well. From inside, it is completely daylit building, and Yash will talk about how much electricity do we consume for lighting over a period of 1 year. But this is on a left hand side you see is a floor where we have research equipment, and on right hand side what you see is mezzanine floor where we have desk spaces. What you see on the ceiling is a radiantly cooled panels. Again, Yash will talk about that in a while. So this is how it looks from inside. And at one point in time, one of our first year sketching professor gave a cross section of the NZEB to all first year students, and that can you really imagine what would be happening inside in terms of thermal environment, or can you really depict the spaces with your own imagination, how light and other things. So this is one sketch one of the first year students, this is first semester student, did about how this building would be operated in a various function. So I will stop here. We were sort of fortunate that university provided us an opportunity to use a land to experiment with, and successfully, rather I would say. So we were a promoter. We did get a funding from various organizations, including Gujarat government and Government of India. USAID assisted us during the design stage, but primarily we were the promoter of the building, and hence we could experiment with many things which now can become a part of the textbook or can be part of the business as usual practices. We also act as architects and designers. Also, Professor Doshi was helping us or guiding us on a design, but primarily we are the one who did working drawings and shop drawings. We worked as a contractor, so we knew what is happening, where it is happening, and what we can expect in the future, including, I won't hide rather, including some places which on first train we got some kind of leakages from the RCC, primarily because of the cold joints and so on and so forth. But we worked as a contractor, and then what is fun now is since about 4 years that we are also operating the building the way we designed it earlier. I will stop here, and I request Deepa to make Yash as a presenter.
Yes, sure. Um, Thank you, Rajan bhai, for this, walking us through the building and the way it's designed and the way the concept developed. I think, could you please mention the area of this building? I think that was kind of
Yeah, so total is about 800 square meter, all floors together, including basement. Yeah.
including basement. Right. So at this point, I just want to, maybe just highlight that although this is a educational building, it's like a research lab, and it's designed, you know, to be designed as a net zero building. However, the concepts that is implemented in the building can be applied to other kind of projects as well, even though if it might be an office building or other kind of building typology. So if you have any questions, I'm telling all the attendees that if you have any questions for the expert panel, please start typing them in so we can start taking them towards the end. After each session, we get this feedback that you have to have a longer Q&A. So if you have questions, please send them in so we can have an extended Q&A this time.
Yeah.
Again,
So before,
thank you very much. Yeah.
Yeah, so before you hand it over to Yash, I definitely want to emphasize one thing that while we were designing it, we were very conscious that although we are designing a net zero building, but it shouldn't look like any spaceship sitting on a land of Ahmedabad. It should harmoniously sit and merge with the surroundings. It should look and function like any other building. I mean, even as occupants, they shouldn't have a burden that they are entering into net zero building. Hence, they need to do 1, 2, 3, 4, 5. So, except for building envelope and systems, everything is a sort of business as usual, including materials. And hand it over to Yash now.
Yes, actually, that's a very good point. net zero buildings need not look like they're completely out of context. They could look like any other building, but it's designed with certain thought in mind. That's a good point. And at this here, I'll just take 1 second to before Yash you start, just to have some interaction and kind of see if people are paying attention. So we have this little poll, and I'm now going to launch this. I think everybody can see this on your screen. Mm, so the question is a good, this building has good daylighting as you would have observed in the pictures and listened into the presentation. So what do you think is the benefit of a good daylighting in building? Does it reduce cooling energy use or lighting or both? Or does it impact either or you're not sure? So start clicking on your systems so we can get your votes and we'll see what everybody thinks. So I'm collecting all the answers. All right, so it's about 50-50. 50% people think it only reduces lighting energy, whereas the other 50 think that it could reduce both cooling and lighting. Rajan, would you like to just explain this? Or maybe any one of you can explain this.
I think let's not answer this. Let's see what this building does,
All right, so
and then
let's
we'll
look
try
at
to
the
figure it out. Yeah.
operation side,
Yeah.
and then we come back to this and see what the impact of good light,
Yeah,
daylighting.
it's always nicer that if professors say something, probably people might not agree to it. So let's see what happens on ground.
Perfect. All right, let's do that. Okay. Now, yeah, Yash, please, you may continue.
Thank you, Deepa. Thank you, Rajan bhai. So I'm a little sad that you don't allow the presenters to click and vote in the polling path. I think you should allow presenters to also vote. You would at least have my vote in one of the third categories. So um, I'll start every presentation of net zero energy building with this slide, which says that every line is the perfect length if you don't measure it. So it's very, very important to conduct performance monitoring of buildings and to understand what is really happening and to compare with what your design intent is versus what it is actually achieving. And without actually measurement, it will be very hard to for me actually to accept that the building is at net zero or highly efficient building. So it's extremely important that we go back and complete the loop, and then hopefully learn that in the next generation of buildings that we are going to build. So once you start thinking about monitoring and the performance monitoring of building and how do you operate the building so you can actually optimize the energy performance of the buildings, you need to start about thinking about what do you exactly want to monitor in buildings. So this list shows what we have monitored in this specific net zero energy building. So we have looked at thermal comfort, which focuses on temperature and humidity. We also have globe temperature sensors at several points so that we understand the radiant effect of the envelope. Visual comfort, we are looking at the visual comfort aspects, how the occupancy of the building changes with time and how does it impact the building performance is another important parameter that we wanted to monitor, and we have been monitoring the outdoor conditions because as it is sitting in Ahmedabad, it's very important to understand what's happening outside, and the equipment usage at a macro level, what's happening on the equipment overall, and what specific equipment is consuming more energy, so that we can then work on using on the next portion in the slide, which talks about building management system, is that once you start monitoring these components, you can start understanding how the energy is being used to maintain comfort as well as to operate the equipment for productivity and efficiency. So this was the prime intent of our strategies, the parameters we wanted to monitor as well as control. In terms of the design, how we looked at 4 different aspects of the monitoring. First, we looked at clear monitoring of components. So we started looking at the envelope performance, how our wall, windows, and roof performed. You saw in the earlier slide how efficient they were and how it performed in the real world. So we started looking at how our envelope is performing, how the indoor environment conditions are, what is the energy use as well as the behavior aspect, and the outdoor component. Some of the equipments that we have integrated in the building. So the building currently has a primary and secondary air conditioning systems. The primary air conditioning system is a radiant cooling system, and the secondary air conditioning system is a VRF, variable refrigerant flow systems. So some of these systems comes with their own control systems, so we don't really have to control it. All we have to do is integrate those systems. So chillers, some of the air conditioning systems, variable frequency drives, which helps us operate the systems at different capacities, and photovoltaic systems, even PVs. We have all integrated all of these different systems into one integrated system. This was one of the key points that we wanted to cover: it keep the building as and operate it as a one integrated system, and not a small different systems which are efficient on its own but may not be efficient as a whole. So that is where the integration part came into picture. In the third divisions, we were talking about control. So once we monitor and integrate, we can start controlling the different aspects of the building: lighting, plug loads, HVAC systems, even looking at whether the photovoltaics need to be switched off in certain portion of the day, or do we have to bypass some of the energy generated and go to the divert it towards the campus as opposed to the building. So those are the aspects where the controls gets into the picture. And finally, display. It's essentially very important after monitoring, integration, and controls, to display the information. So in a daily basis, we have an information of how building is operating, what is the comfort level inside the buildings, what is a daily consumption versus generation, as well as historical trends and the benchmark, that how building has operated last year's versus this year's versus a few years ago. So this is how we divided our own monitoring strategy. This is a little bit more in the next slide shows in details, how we went about implementing our strategies. So all the energy meters, chillers, VRF, and digital scrolls, and even some of the envelope components, we just use the communication gateway to integrate the systems, while some of the things which did not have sensors, we actually have installed our own sensors, our own controllers, and integrated that into a building control system. We also looked at the 3 tiers of the building management system. First is the field space. So the energy meters provide us the information of what's happening at a component level, and then we integrate into a network communication tier where the information from the field sensors or field devices integrate into a one centralized system. And then we have several wired devices as well as wireless devices, which will help us then cover a diverse set of measurements in the building. The location of these sensors were also very strategically selected. So you can see on the sensor location example screen that the red dot shows all the sensors at different points in the building, so that we can understand if one part of the building is overcooled versus other part of building is hot, and you can identify cold and hot spots and accordingly control your air conditioning system. Also, it was also linked with how the systems are placed. So one of the system was placed near 11, 12, 13, 14 points, so you will have a sensor closer to it, so that you can actually control and modify operation of the systems, and the impact of that will be imminently seen on the sensors. This is a screenshot of our building management system. We could not actually get the kind of graphics and the interface that we were looking for to effectively operate our monitoring system. So our in-house team actually designed this interface for the building management system. In here, the top box on the left side shows the outdoor conditions and the entire building energy consumption. So you'll see the outdoor weather station conditions and energy is the focus of that box. The second box on the left, which talks about shows the floor plan of the building and of each floor of the building: basement, ground floor, first floor, and mezzanine, where you can clearly see at the screen and understand what is the temperature, relative humidity, and energy consumed by this particular floor of the building. So you can very quickly keep looking at the screen and understand how the building is being operated and make decisions. If, for example, there is no meetings happening in the basement floor, which is primarily a conference room, you would immediately notice that that air conditioning system should have been turned off. On the right side, you'll see other two blocks of the other two systems. The top one on the right side shows the radiant system, dedicated outdoor system, VRF system, fan and lights. So you will see what the air conditioning systems and the fans energy consumption is instantaneously at that time during the day. And the last box on the right shows all the research equipment that we have also integrated with the building management system to understand if the overall energy consumption is higher, if is it because of the radiant system operating, or is it if we have one of our research equipment that is a research experiment that's going on. This is another screenshot of the building management system where you will see we have temperature, relative humidity, and as also a carbon dioxide level in the space, so that we can effectively control the carbon dioxide level in the space by operating the ventilation fans as needed. This has worked very well in effectively managing only the outdoor air quantity that we need for the building. So for example, if we have lesser number of occupants present in the building, and we would turn off the ventilation fans so that our energy consumption reduces, our outdoor air quantity reduces, uh, but however our CO2 level stays within a limit below 1000 parts per million. And when our carbon dioxide level goes above 1000 parts per million, then we start additional ventilation fans to ensure that the indoor air quality and health of our occupants do not get affected. But at the same time, it increases the energy consumption of the building. So we are currently monitoring it's a research building, what we call as it's a living laboratory, where we are not only studying different components of the buildings, but we are also studying how buildings operate. So the building itself is a part of our study, and so we are monitoring about 1,000 points, starting from indoor environment, consumption, generation, outdoor conditions, and different end uses at the floor level, even at the occupant level, to understand how the energy, where the energy is used, and how we can optimize it. While this is a significant number of points, we have also worked on a research where we have tried to minimize the number of points that are needed to effectively use the building management system without really going in the real world. You may not have to have so many number of points for efficient operation. We have identified how many number of points are needed to make the buildings to effectively monitor buildings and optimize the energy performance of a building. So here are a couple of screenshots where how the building system energy management system, where the building management system is located, and the visitors, when they come and visit us, we show them and give all these facilities, show them how the controllers look, how it's operated, and they get full access of how the systems look. In the next 8-10 slides, I'm going to talk about the actual monitored data that we have derived from the buildings. As I said earlier, it's very important to actually monitor the performance of a building. The blue bars show the air temperature that we have observed. As you can see, we have observed throughout the year about 45 degrees to a temperature of 18 to 12 to 13 degrees throughout the year, and humidity as high as 99%, which probably means raining, to very low dry humidity of 10-20%. So the building has experienced a wide variety of temperature RH conditions. Next, this slide shows our observation in the surface temperatures of window and roof in the building. The gray bar shows the exterior temperature, which goes as high as 65 degrees as expected. But you can see that inside, even when the building is unoccupied during 13th to 15th May, the roof interior temperature, the black line shows that it is only 33 to 34 degrees. And as you can see, when the buildings are operated, it again dips down further. So it shows that the insulation has worked really well in insulating and reducing the outdoor heat that is coming inside the building. I'm going to browse these slides very quickly because it's a lot of information. Each slide needs a lot of time, but I'm just going to highlight the important key point in the uh, um, uh, in the topic. In the next slide, I'm talking about just showing the what we have observed during a typical summer week. Um, the yellow line here shows the outdoor temperature, and the black line shows that we have uh, the indoor temperature. As you can see, the black line drops during some part of the day when the occupancy starts and we start the air conditioning system. There are a few things important to observe. You can see the red bars, the histograms sort of look where you can see how the energy generation is occurring in the building, and there is a shift between the energy generation versus energy consumption. Energy consumption, HVAC energy consumption, is in the blue bars. So you can see, that the generation is happening during the earlier part of the day, while the consumption is all continuing to be there even in the later part of the day. So these are some of the things that we have been observing and trying to optimize the system performance. Going to the next week, a typical winter week that we have observed. Now here you can see the generation bar has actually increased. So you can see that the generation remains a little bit at the same level, but slightly higher because the efficiency of the photovoltaic panels reduces as the ambient temperature increases. So in winter, it has a very comfortable outdoor temperature. You can see from 25-30 degrees, 20 to 30-35 degrees, and so the energy generation increases, and as expected, energy consumption, HVAC energy consumption, significantly reduces. Still, there is a phase lag that continues between the generation that we get versus the consumption that we consume in the building. Going to the next slide, this slide shows the map of the building of hourly energy consumption. So you can see this is a heat map where the scale below shows the kWh consumed per hour, varying from 0 to 30 kilowatt per hour. You can see that there is in the month of June, there is a line there which shows the highest energy consumption we have observed in a year, and you can see in the month of January, and it's very low. In February and December time, it's slightly higher but still quite low. And up to February, March, we have a reasonably low energy consumption. Starting from mid-April to July is when we use a lot of energy. But also during the summertime, we have to use a lot of energy to provide to counter to the latent loads or the moisture loads that comes during the monsoon seasons. So you will see that there is a different kind of behavior of the same building. So to counter the moisture load, we have to start running the VRF systems, because radiant system primarily caters to the sensible loads or only the temperature, but for moisture load we have to work on we have to turn on the VRF system. So there is an additional energy consumption you will see in the month of August and September. The next slides are going to be slightly easier to read, I hope. In here we have divided the whole consumption and generation in a monthly pattern. So this is the monthly energy consumption that we have observed. The blue bar shows the energy consumption, and the red bar shows the energy generation. As you can see, the energy consumption, monthly energy consumption, increases and maximizes in the month of June, and again it starts reducing after that. Again, as we have seen in the earlier heat map, the August and September also has slightly increased energy consumption. But the generation, on the other hand, peaks at the March time. This is when the ideal conditions in terms of the temperature exist, and solar radiation, although it will be the radiation in the March will be lower than May, it still produces more energy because of the higher efficiency of the PV cells due to lower ambient temperature. So May is really too hot for PV panels to generate energy. Even though the solar incident radiation is high, the efficiency is lower because of the higher ambient temperature. Then we did a couple of analysis just to show how the relationship of the outdoor temperature is with the daily space consumption, and you can see that the blue dot shows the winter dots, the yellow shows the monsoon dots, and the red shows the summer energy consumption. And you will see a moderate relationship between the outdoor temperature and the indoor temperature, indoor and so daily energy consumption. If this graph is steep, so if you see a very steep graph towards the 45 degrees relationship, that means that you actually have a very less tight building. A lot of impact is happening of the outdoor temperature in the building energy consumption. In an ideal scenario, you would have flat line where the outdoor temperature has no impact. Maybe not an ideal scenario, but that's one way you can say that there is no impact. But this here shows a moderate relationship. So even after insulation, some heat gets in when the outdoor temperature is high. Again, going to the next slide, this shows the indoor temperature versus outdoor temperature relationship. So each dot shows a temperature of an hour, indoor and outdoor, for three different air conditioning systems. So since when it's really cold, we operate a lot of times a radiant cooling panel, or we operate only the VRV depending upon which unit is efficient. And sometimes when there is a peak load, then you have to operate both VRV plus radiant cooling system, or if you have a high moisture load, you have to operate both VRV and radiant cooling system. So this graph just shows how the scatter plot is for different indoor and outdoor conditions. You will see that when you are operating the radiant cooling system, you will see a very flatter curves compared to when you will see in VRV systems, where you'll see a slight slope with an outdoor temperature. So that is where you can see that radiant cooling system, the indoor temperature remains very uniform, or it does not change as much as the change occurs for the VRV systems. The next slide, I'm going to show just the breakup of the end use that is used by building. So the equipment, which means the research equipment used in the building, use about 15.5 kilowatt hour per meter square of energy. The air conditioning system, which uses the maximum in the building, is 24.1 kilowatt hour per meter square. As Rajan Bhai said, the lighting energy use is significantly low, which is a 0.1 kilowatt hour per meter square, which is commendable and a great tribute to the people who did the daylighting design for the building, because the building is completely daylit, and that's why we are only using 0.1 kilowatt hour per meter square. And the plug load, which is computers, laptops, and all the printers, all the other office equipment, uses 2.7 kilowatt hour per meter square. In the next slide, I'm going to just talk about what our design goals were. So as Rajan Bhai said, our design goals were 58 kilowatt hour per meter square, but our actual consumption was 42.5 kilowatt hour per meter square. And the generation is 51.2 kilowatt hours per meter square. This is an annual energy consumption and annual energy generation. And so the building has operated to be 8.6 net positive kilowatt hour per meter square. And this is where we can go back and say that, what we designed, what we intended to do, and what we constructed, and what after operation, this is what we were able to achieve in the net zero energy building. Few other slides I want to talk about that. While we have all only talked about energy consumption in earlier slide, it's very important to understand what the occupant comfort is. Finally, if I can turn off the air conditioning system and show 0 kilowatt hour per meter square, but are the occupants comfortable in the space or not. So that's why it's very, very important to keep track of that. So we take surveys 4 times a week, Mondays on Mondays and Thursdays, 11 o'clock, and it's 4 o'clock in the afternoon, to take a survey from occupants how comfortable they are. They have a choice to adjust the set points. And we also note, the temperature, relative humidity, mean radiant temperature, clothing that have been occupants are wearing, and their activity level met. Have they been working on a research equipment, or they have been sitting and working on the in the lab. There is also personal fans and the pedestal fans that we have provided for the occupants to adjust their local environment, which gives us more flexibility to adjust the ambient temperature. And this survey focuses on 3 points: the sensations, thermal comfort sensation, satisfaction. So sensation is based on 7-point scale, 1 to 7, whether it's most comfortable to most uncomfortable, very comfortable to very uncomfortable. And satisfaction shows only 2-point, whether it's acceptable or not acceptable. And preference against talk about whether you want to you are comfortable, but do you still want to modify any of the parameters in the building. So this graph on the or the image on the left shows that what was the survey that we have received on the peak week of the or the summer week of the year. And the blue, the green bar shows how many people were comfortable and very comfortable. The light green shows how many were just comfortable. Red shows that very uncomfortable. And we have some researchers which are moving for research projects, traveling. So there are some data on some days we don't have any feedback from there. So from that comfort survey and the measurements, we have plotted few graphs for everybody to us to understand how the temperatures are inside the space. So the India model of adaptive thermal comfort that has been developed by our research team, which has also been adopted by National Building Code, shows the bar that within which the occupants are expected to be comfortable based on the survey data, and the red dot shows the actual dry bulb temperature that we have observed in the field. So you can see that the dots are actually very close to the 90% upper limit of comfortable, and sometimes going into the 80% limit. The next slide again is dividing the same data into a different way. So the red dot shows the information of the unacceptable. So people who said that this temperature is unacceptable, what was their sensation watt, and how many people said it's acceptable, what was their sensation watt. So most of the people who said that the temperature for some reason is unacceptable, they have a very almost a neutral vote. So this is where we had to look into saying that even though there's temperature is meeting, do you still have to increase the air velocity? Do you have to increase have the pedestal fan in the building so we can increase the acceptability of our building? And the blue dot shows on the top what is the range of the thermal sensation watts we have observed in the building. And this is the slide where we have looked at the temperature bins, whatever the observed temperature inside the space, number of votes we have received. So that also links to how many times that condition occurred in the building. So you'll see that we have certain temperature about 500 or 600 votes that we have received, and what fraction of those votes were showing that they are comfortable. And you can see we have almost have been able to maintain more than 90% acceptability in all the temperature range, even at a very high temperature, because of the air velocity, higher air velocity, and the pedestal fans. We have still achieved a very high votes on that the occupants are comfortable. In the end, I would like to thank the partners who have gone way beyond their contract and worked actually with us in building the net zero energy building and really achieving the net zero building at our facility. And that's all I have right now on the operation data. Thank you.
Thank you so much, Yash. That was really comprehensive, and I'm sure there is like millions of data that you have, and it's quite something to present just the important and the pertinent ones in a presentation like this. It clearly shows how the building is functioning and the thermal comfort as well in the building. In fact, there are so many questions coming in. I thought I could also ask you a question, but I think I'll not, and I'll directly start taking the questions from the audience. Just a second. All right. So let's jump into the questions. So I'll start reading them, and then one of you all can answer. The first question is, can buildings of different scales and application target net zero?
Hi, so this is Rajan again. I think different scales, definitely you can achieve net zero, provided you have enough capability to generate. You definitely can downsize, sort of rock bottom downsize, but certain application, even if you rock bottom downsize, you might not be able to generate enough. And these are the applications where you have a high process load. So if you have a high process load, like some of our equipment, if we keep using them for 250 days plus, then definitely it would be challenging for us to reach to net positive or net zero. So scales, yes, possible. Application, you need to be selective.
Right. So reducing demand is the key thing that we need to really look at.
Yes, that's right.
Next question is, what was the criterion to keep the CO2 level trigger point at 1000 ppm for outdoor air exchange when it's recommended that indoor period should need to exceed 700 ppm of CO2 for sustained periods?
That's a very good question, actually. So different ASHRAE standards have different threshold limits, and it's very clearly defined. We have gone for a slightly more aggressive or slightly more conservative, I should say, 1000 parts per million. But ASHRAE has a very clear threshold for different types of buildings. Like office buildings, you'll have a different threshold. It can vary from 1200 to 1500 or up to 2000 parts per million, depending upon how stringent you want to go to. But the standards can give you a good idea of where what kind of occupants are there, and accordingly select the threshold, and that can be used as our threshold to control the indoor air quality.
Right. The next question is related to this actually. When it is too hot outside, is the indoor air still exchanged with the outdoors to maintain a favorable CO2 level?
Yes, so the answer to that is health is a first priority in terms of the control algorithms, followed by the energy consumption. So whenever the safety of the occupants come into the picture, for example, the CO2 level is higher than 1000 parts per million, that was our threshold, but it could be different above the threshold level. We would still bring in the outdoor air so that the indoor CO2 level is below 1000 parts per million. The moment it is below 1000 parts of million, then we start modulating the outdoor air or reducing the outdoor air quantity or outdoor air exchange so that we can optimize our energy consumption.
Yeah, just to add on what Yash stated, and generally the question is how do you really do this? So the CO2 management in outdoor, when it becomes too harsh outdoor, we basically shut our windows and start relying on inlet fans and exhaust fans to manage air exchange and CO2 levels. So that's how we do it, and not just relying on windows.
Right. Next question. You mentioned that this is a mixed mode building. The windows, are they operated mechanically or they're just done manually?
Manually.
Okay. And then the next question, is the building used 7 days a week?
Rather five and a half.
Okay.
Rather 6 days or 5.5 days, not all 7 days.
Okay. Next question. Any reason for not installing ceiling fans?
Radiant ceiling and a ceiling fan together we thought might not be the best option. And hence we rely on horizontal air movement and then the vertical air movement through ceiling fans.
Okay. Next question. Can space heating during winters also be achieved naturally without heating coils or heaters?
We don't require heating inside the building during the winters, at least between 2014 and 2019. I don't know what's going to happen in the future.
Okay.
Yeah, and you know, during winter, because outdoor conditions are not, it's cold, and you're less likely to have a natural ways of providing heating, and that's like an extreme condition in summer, like a winter when it's cold inside, you will have to use the heating modes of the air conditioning systems to provide the comfortable environment. And as Rajan Bhai said, while the system is capable of providing the heating, we have not needed that because the building envelope is tight and the air exchange is also really less. So we have been able to not need the heating system for the building.
Okay. Next question. What was the chiller size for the Radiant and VRF? Was it difficult to find chillers that would work at such lower loads and then part loads?
That's an excellent question. That's definitely very hard to find a chiller. So the capacity of those chillers are 8 tons uh, for the entire building. We were able to find chillers which were on-off chillers, but not, we were wanting to have a inverter or a variable capacitor chiller. So even at when we have only 1 or 2 tons of load, the chiller can actually turn down the energy consumption. So it was very difficult. Fortunately, we had found a few European manufacturers where with some effort, we were able to engage them and they could provide us the chiller of lower capacity, but still inverter chillers, which reduces the capacity consumption of the compressor, turn down the compressor capacity and such, so the energy consumption. So we have been able to find that.
Yeah, although the discussion is based on capacity of chiller and whether they can function at part loads and whether we can find that or not. One more challenge which we face that even, I mean, the moment we spotted a chiller which is of 8 ton and the specification was kind of chiller which we really wanted, challenge was that will it actually communicate with our BMS system and whether they will allow us to do that or not. So it's not just about the capacity and whether it can function at part load, but you also might need to face a challenge that will it talk to BMS, which you want.
Right. Okay. Next question is, how many occupants are there in the building?
33 to 34.
Okay.
And a
Any?
conference,
Mhm.
sorry, we have a conference room in the basement which can house 60, 70 occupants. So on a given day on the top researchers floors, like Rajan Bhai said, we have 30 to 40 occupants, but on the depending upon the conference room may have 60 to 100 occupants for an hour or so.
Right. And if
Yeah,
you could,
so on probably about 60, I mean, minimum 60 days and maximum 90 days of occupancy for the seminar rooms where we have 40 to 60, 80 people.
okay. Okay. So I think the next question is sort of related to this. Any strategies for accommodating future occupants? I guess this means if the occupancy increases, the staff increases, and still maintaining net zero.
No, we don't have a space to accommodate. So we are very happy that we have reached to a level and still we have managed so that we don't need to think about future.
Okay. Next question, what is the peak capacity of the PV system?
30 kilowatt peak.
Okay. Actually, it was quite interesting when you were explaining that it's not necessary that in summer when you have the maximum radiation, the output is the maximum. I mean, the efficiency does go down. And I think your Jan data also showed quite high generation.
Absolutely, and that's different. It's a significantly different when you look at the, when you look at the European climate or American climate. This is very typical for Indian climates, where you will see winters is the best period to harness, and that's why it's a net zero energy building, that you get more in winter, and then you compensate for the energy consumption that you have used in the summer.
The data which Yash showed was, I think, of 2017, but what we have observed in 2018 as well is that March, April is a time when we get a good favorable condition for generation. Although January, February could be better, but because of the high suspended solid particles in the air, we really don't get a good sunshine hours. And that's what the urban India is right now facing, as all of you know.
Okay, okay, that's actually very insightful. Next question is, in winters, temperatures seem to be quite high inside, as apparent from your results. Did you achieve this without heating? I think they didn't see
Yes.
the number
No.
properly. It's pretty
Yeah. No.
comfortable.
No heating. Yeah. No heating. I won't. That's what I just wanted to correct. That it wasn't. The temperature were not very high. Temperature were comfortable.
Mm, right. Next question is, what kind of occupant controls there are in the building?
Um. The occupants can use the pedestal fans as and when they need. They have a task lighting, and they can operate windows if at all they need to. At that point in time, we need to work on our HVAC system. But those are the occupant control. There's nothing sophisticated about control system and occupants.
Okay. After all, next question is, after the building was built, did the operations team undergo extensive training to actually monitor and operate the building? Because there are so many sensors in the building.
Yeah, so that's what the fun of doing job at CEPT is, that you learn and you earn, and that's what we did.
Okay. And um, this question is from me. Last week we
Before
had this.
before Deepa, before you go there, I think in terms of a common building, you would need a, facility manager is a very important team, and that is why their training is very important, because no matter how good you have used equipment, built equipment or installed it, your energy consumption has a direct linkage with the knowledge of your facility managers. And so, as
Yeah,
Rajan bhai
yeah.
said, we have a research team who knows about, inside out of the building physics, and they can work on things. This is an area that somebody who wants to build net zero energy building should try to get a good facility managers in place.
Yeah, and this is Rajan again. I think we took about at least 14, 15 months before we started operating everything in a sync with each other. So initial time there was learning from our side as well, especially how to manage the condensation and how to manage the CO2 level, when to operate a VRV, when not to operate VRF. And now I think we are very confident, because even for us it took a while to understand how envelope is functioning. Envelope is so optimized that we sometimes earlier we thought that we need to run the system, but now we think that no, because the envelope is well optimized, we really don't require to run the system, and that function on its own. So definitely about a year plus is time which you need to spend actively on managing the building before you start operating them, and
Right.
documentation of that. And very important is the documentation, because if you have a change in a team member, now it's you definitely need to pass on the knowledge to the another guy. So the way you document it helps the next person to take it over.
Right, absolutely. In fact, the point that you mentioned about optimizing the building envelope, that brings me to this question. You know, in my interaction with other professionals, especially architects, whenever the conversation for net zero energy building or high performance building comes up, there's this thing, there's a little panic that sets in, and they immediately kind of respond like, let's not go there. It's too expensive and it's too far-fetched an idea to achieve. Whereas the point that we're trying to make in this webinar is that the envelope is really optimized, which is really in the scope of architects. So from your experience, what would you like to tell these group of professionals, and what would make them engage more with the NZEB conversation?
I think envelope optimization is not very challenging task. I mean, you definitely can achieve 85%, 90% of a good design if you have a common sense and if you start relying on some of the scientific literature and bit of numeric simulations and so on and so forth. So it's not really very difficult if you sit with a mechanical engineer or person who can do a good heat load calculation and start doing sort of conversation with him. Challenge will come in the last 10% where you really want to stretch yourself and achieve a net zero, and what target do you really set up. There are net zero buildings spread over acres because they have a place to generate enough through solar photovoltaic, and hence they could, without doing a much of optimization, they could achieve net zero. Yeah, that's one way of doing it. But if in a business as usual urban setting, if you really need to achieve net zero status, envelope optimization is very good. And last 10% definitely is where you need to spend time. Now that comes to a point where how much cost. Definitely it will add a cost, about 5% plus here and there, depending upon which climate you are in. But then again, at the reduction at the capacity of your system definitely will benefit you. And we also need to understand, and sometimes this, just to let people understand, that it is very important for us to know what is the cost of not doing it. And I give this example of either a toothache or a headache. And I mean, you do have a toothache, and you said, okay, let me not go to dentist today or tomorrow, and you keep lingering, and then you don't know what the cost you are paying at the end of 5 days or 10 days or 1 month. And that's the kind of cost which we don't know what cost are we going to pay if we really don't work on energy efficiency, and then second tier of that, which is a net zero. So it is important that we also look at the what are we paying obviously and what we are not going to account with a certain kind of I would say not knowledge with us kind of situation.
Right. Yeah. That that analogy was really good, and I think it really drives the point home. With that, we are pretty much at the end of the session and end of the webinar. I thank you, Rajan Bhai and Yash. Thank you so much for your time and sharing your insights. And oh, that was a very clear and concise presentation, and I'm very sure the attendees are taking away a lot of valuable, you know, uh, things that they've learned and things to take away and apply at their work. With this, just one thing. All these case studies, which is the CARBSE building and other case studies, you can find on our website, netzeroenergybuildings.in. If you haven't already, please do visit the website and sign up on it so you can receive updates, and connect with us on social media for all the updates regarding NZEB. And next week, we will be back with another topic, which is daylighting technologies. And that's also an interesting thing to look at. What are the different cutting edge technologies available to enhance daylight in buildings? And that's next week on 2nd. And again, if you haven't already known about this, we are already conducting an NZEB contest, and that's on rainwater harvesting. All the more appropriate now that we are actually having a dry spell. Look around and see what are the different rainwater harvesting systems that you can find. Click a picture and post it on your social media with the hashtag NZEB India. Let's try to look around and observe what we are doing with the rainwater. And with that, thank you so much for joining in. Thank you very much, Yash and Rajan Bhai as well. And I will see you next week.
Thank you, Deepa. Thanks, Maitri and ADS team. Thank you.
Thank you.